So I recorded last session and I put it on YouTube. I just posted it in Canvas. I haven't figured out the best way to do that in Canvas yet because I thought I could make a module and link it to a module or something like that. But I think I just started a discussion. So it's there if anybody wants to rewatch Tuesday's class, and we can use that as a discussion if there are any questions for the material we covered. Tonight we will. I have some material for us to go over. Primarily, I'm pulling all the stuff out of Chapter 2 from the book, but hopefully it'll be a short evening. And if anyone wants to talk about Docker, Postgres, etc., after we finish material, then we can certainly do that. And on that, I will get started. So chapter 2 in our book is all about why we should worry about database designs. It's essentially the chapter in the book that tells you why you should buy the book. It talks about the reasons it's good for our business, reasons it's good for our applications and our data. And so let's go through this material fairly quickly. Because it's literally verbatim from your book, from chapter 2 of the book. So why should you be concerned with database design? We talked about last week for our relational databases how we have consistency and rules built into our data, and using a relational database can guarantee that you will not lose data. The data is as you thought it would be. And so designing this system is critical so you know what data should be in your database, and there are guarantees for persistence and for data existence. Inaccurate information is probably the most detrimental result of improper database design. Things can get so complex, even if all your data is there, you'll get into times where the complexity of your SQL queries, the complexity of your database relationships, the subtle cases in your data. If you're doing data analysis, it could just get really confusing. And the worse it's designed, then the easier it is for you to make a mistake when you're looking at data for your company. And so I think this sentence ended with, and this could conversely affect your organization's bottom line. Relational databases are still heavily used for finances, for accounting purposes, transactions on a website, inventory management, these critical core business capabilities that if you get it wrong, it could have a big impact. Bottom line is kind of the ultimate impact, but it could be customer dissatisfaction. It could be regulatory audits that are given the wrong data, which could result in fines or punishments by a regulatory agency. So the reason we go through all of this design process before we even touch an actual database is to make sure we know how to design them well for all of the different scenarios we'll be hitting for with our databases. Yes, sir.
Talk about relational database. I was having some thoughts the other day. In my industry, now people are talking about graph database.
Yep.
Is graph database to any extent related to relational database, or it's part of, or it's a type of relational database, or it's totally different? What's the driver for having that?
So what industry are you in, out of curiosity?
I'm in the power industry, electric power. I work for the university.
Uh-huh. All right, well, first, try to figure out how I can get power to my shed. They won't call me back. But anyway, so graph databases, I did a video series, educational series for a publishing company on graph database technology. So I'm fairly well versed in that area. A graph database is primarily built for relationships between objects, I guess is the right word. I forget the word. It's been a while. Nodes. Yeah, you have nodes and edges. So a node is a thing. So you could almost think about a node like a record in a relational database. And the edge, or the relationship, is how it is related to other nodes in the database. So there's really no concept of a table. There's really no concept of normalization of data. It is primarily built for finding multi-level relationships, or the connections between those nodes. So one of the prime examples of how to use a graph database, or when you could use a graph database, is the whole 6 degrees of Kevin Bacon. You know, the old theory that any actor is only within 6 degrees of being in a movie with Kevin Bacon. And so it's those kind of relationships that are best suited for a graph database. And if our time goes well in the semester, I was hoping to get to a quick overview of graph databases. All that being said, Postgres, that we'll be using heavily, has a graph database capability built into it, but it's not a relational database. It's kind of another thing that the database can do. Now, you can model graphs in a relational database and all that stuff, but they're not purpose built for graphs.
Thank you.
Great question. Advantages of learning a good design methodology. It gives you the skills you need to design a sound database structure, avoid duplication of data, redundant data, invalid data, guarantees required data and relationships. This is like any other practice we have in our life. Anybody could probably go out and build a car, but if you wanted to go build a car, you'd probably learn how to build a car first before you actually did it. And it's the same thing here. We're learning a pretty traditional methodology for designing a database, or identifying the data you need, or the relations you need in your database, the data you need in your database. So we're going to be spending a lot of time on a process to design a good database. And like designing anything before you build, it's going to help you save time. It's going to help you from making mistakes. And I like the last bullet in here from the book. It helps you understand your data and domain better. If you take time ahead of actually building something to plan how to build that thing, odds are it'll end up being better. You know, cars, houses, databases, it's all the same. It's plan how to build it before you build it. So the objectives of our good design. When we think about data that we use at work, you have the data you need. You need the list of the most recent orders. You need status of associates. You need the things you're going to be querying your database for. Databases grow and change over time. And a lot of those changes happen from what we call ad hoc querying, meaning it wasn't something we planned ahead of time. It's kind of what if the data could tell us something? So this is where those relationships come into play, storing extra data that maybe you'll use someday. The better we organize our databases, the more flexible they're going to be. And because of that, we'll be able to find data that we didn't expect to find later. Tables are constructed properly. The reason we build tables properly is primarily around efficiency. So when we talk about building our database tables, we'll talk about how do we index the data for faster querying. We'll talk about business rules that we can apply to the data within the table. Those things you're planning ahead of time before you actually build your tables. And future growth is so much easier on a database that is built well from the beginning, instead of trying to bolt on something to a poorly designed system. I know that's all kind of high level why we're doing a lot of this stuff, but anybody have any questions on it? Or does all this sound make sense to me? Yeah.
Makes sense to me.
There you go. I like interaction, so feel free to ask questions. All right. Benefits, I think I talked about these a lot. Data is easy to modify. Information is easy to retrieve. We're going to make a clear distinction on data and information. The idea is that data is typically a point in time. It's a measurement. It's a status. It's data. It doesn't mean anything. When we start to analyze our data for a purpose, that's when it becomes information. It's information that we can use to drive a business decision. It's information we can use to analyze a current scenario. We will get more value usually from aggregate data as opposed to a single data record, depending on the scenario. And so it's that analysis of your data is when it becomes information, and the information is really what's important. And the better we design our database, the easier it's going to be used for any application that's built on top of it, whether it's a user application, a mobile application, web services. The more standard and structured our database is, the easier it's going to be to understand by developers. And so relational databases that we're going to talk about this semester are strictly structured. They have data types, they have required fields, they have relationships that are enforced by the database engine. These are advantages that a relational database gives you that other databases don't. Other types of databases don't. So as an example, I'm a huge fan of Elasticsearch. It is a full text search engine document database. The data is organized by document type, which is almost like a table. Data has columns or attributes like a relational database. But you can't set rules. You can't say this must be a integer greater than the number 5, or it can't be less than 0. There are no relationships between the data. You can't say this person is related to these pets or houses or whatever relationship we're trying to build. The constructs just don't exist in those databases, and there are reasons for that. And so it changes the way that we have to think about data. And so depending on the problem we're trying to solve, we have to pick the right technology for it. And relational databases are kind of the backbone of structured data, of data that is important, data that can't be lost, data that must comply to a schema, all these things. So relational databases will never go away, in my opinion. People talk about NoSQL being kind of the new future hotness, and it'll take over the world. And to some extent, that's true. A NoSQL database has advantages that a relational database it's really hard to do, such as scaling databases to be billions of records, billions of users. It's really, really hard to do that with a traditional relational database because of those advantages, like the data consistency and the relationships. When you're only modifying one record that has no relationships, that can scale really easily. But once you've got those restrictions, it's a lot harder to scale. And so database design will help us do that. And we'll talk about all that. So when we go through our traditional design, this is going to look like anything you've talked about, for whether it's software processes or data processes or building standards at work or building processes at work. The first step is always requirements analysis. And the whole purpose there is to figure out why we're going to be building the database that we're going to be building. What are people going to be using it for? What data do we have to store? So if we're building a e-commerce backend for supply chain management, or for counting supplies of objects, we're not going to be worried too much about users and the notes they took on their computer yesterday. We're going to be looking at the domain of supply chain or the domain of warehouse management. So figuring out what the people in the warehouse need is the requirements analysis. Do they need to have the ability to have multiple SKUs for a product. Different vendors have different products, but they're maybe the same product. And so going through the analysis of what your data is going to be used for is really the first step. And typically we do that by talking to folks in a business function who are the expert in their domain. So we wouldn't talk to the head finance guy about how to model a database for manufacturing a car. He might have some input, or she might have some input, because cost associated with parts is probably important. But your primary drivers there are going to be the ones who are going to be using your database for their primary function. And so understanding the business need for this database is requirements gathering, and that's always the first step. After that, it's figuring out what data you need to store. So this is where we start thinking about primary keys, and we start thinking about uniqueness of data. We start thinking about the rules around the data. Like a transaction can't be below $0 because when you're buying something, that doesn't make sense. And so this is where we start getting into diagramming our databases, which is the next topic we're going to talk about. How do we plan the data in our database? How do we plan those relationships? How do we plan the data types? I forget the word they use, and it's on the next slide, so I'm tempted to skip ahead. But the characteristics of those relationships. Last week we talked about, or Tuesday we talked about one-to-one relationships, one-to-many relationships. So that's a characteristic of that relationship. And so figuring all that out that's your design or your data modeling process. Normalization is almost a optimization phase when you're building your database. So there are ways we can model data very poorly. We're going to talk at length about this, so I won't go too deep into it. But normalization is a set of rules for how we model the actual data in our database, so we can avoid inefficiencies, we can avoid duplications, we can be more efficient with how we're storing, querying, and updating our data. So one of the ways that we design and we share designs of our databases is by building ER diagrams. They're called entity relationship diagrams. This helps us visualize, it helps me visualize, what our data is going to look like. We can use this to represent the tables, the table relationships, and those relationship characteristics. So as an example, last week we talked about agents and clients being a one-to-many relationship. So if we look at this diagram, the first horizontal section is an agent's table. In this diagram, we're not showing any fields, any attributes, no primary keys, etc. What we're showing that we have an agent relation. That relation is going to be a table in our database, and it is related to our client's database. So you'll see a couple notations on here. The first one being the diamond with the 1:n. That's saying it's a one-to-many relationship. So that drives a couple of things. That drives the expectations of what's going to be in our database. That drives how we actually build that relationship within the database itself too. There are different ways you model a one-to-many relationship, a one-to-one relationship, or a many-to-many relationship. So someone can design a database using this kind of notation, and the next person can take that design and turn it into an actual database. They can write their actual data definition language, their DDL scripts for their database to create the actual tables and relationships. On the right-hand side of that, next to the crow's feet, I think is what we call them, connecting to the clients, the circle and the multiple feet mean that this is really a zero-to-many relationship, not just a one-to-many, like more than one or more, but it's actually a zero or more. If that circle was not there, it would represent one or more. And the same thing for the bottom one. We have our staff entity or a staff relation, and the one-to-one relationship called out on the diamond. And again, this circle means 0 or 1. The vertical line on the horizontal connector means 1. So that is a one-to-one relationship. The circle makes it an optional one-to-one relationship, so a 0-to-1 relationship. Any questions on this? I have the next slide talks about all the different combinations of crow's feet and circles and lines and stuff. But so far we've talked about any questions, concerns, thoughts? We're rolling through this then. So your many options. So when we're doing these ER diagrams, the project that we build throughout this semester, one of the first stages is, after the documentation and requirement of what your data model will do, is to build an ER diagram. And as part of that project, I will be looking for using the right labels or the right diagramming when we do it. And so these are important when we have a one-to-many, one and only one, 0, 1, one-to-many, 0 or many. I feel like my picture got cut off. Many-to-many, we put the crow's feet on both sides of the line, because it's basically a two-way relationship. I'll check to see if my picture's cut off later, and I'll shrink it if it is. Yep.
So the earlier slide, can we go to the earlier slide?
Which one?
The one earlier than this. Just the one earlier. Yeah, that one. So the relationship between staff and workplaces, does that mean a staff can either have a zero workspace or one at max?
That's right. That's exactly right. Yep.
So realistically, how is that possible? Like, I mean, if the staff works remotely, then that's possible. If the staff works on site, he or she has to have a workspace, right?
So it's an example. It doesn't have to be a realistic example. But yeah, I don't have a VCU workspace. So VCU wouldn't put my home workspace in their database, because it's mine, not theirs. And so if I had an office on campus, then I'd have a workspace. So I think it's a reasonable way to model a workspace and a staff. And even more so than that, like I know our new interim department chair has 2 workspaces. So it's not a perfect example, but I figure it's easy enough for explanation purposes. But it's a great discussion, because those are the discussions we're going to have through the semester when we talk about examples of business problems that we're going to solve, and we're going to argue with each other on how we're going to model it, because there is usually not a perfect answer, or more than one scenario could work out, right? Because in this, again, going back to this staff thing, 2 people could share an office. So really, it's a many-to-many relationship.
Right.
So, yeah, it's good point.
I had a quick question about the connectors.
Yep.
What's the difference between using the one and the one and only one?
So one and only one means it's a required relationship. So let's imagine we were modeling a person. So I am a person. I have attributes like a first name, middle name, last name, birth date, primary home address, all this kind of stuff, right? In our database, as an example, we could, for efficiency's sake, we could model let's say our primary residence, right? Not just like the houses we own or apartments we live in or whatever, but let's say our primary residence. Every student, every faculty must have a primary residence or a primary mailing address or something like that. Now, multiple students could have the same address, so now we're starting to talk many to many. But if we keep it simple, we have options. So one option is we have a single table for the user or for the person, and in that table we have attributes about the address because they have one primary address. That's an option. Second option, we model two tables. One is about their person, things, first name, last name, birth date, etc. And a second table is a primary address table where it has a foreign key to the user, and that we store all that data in a separate table. But because of our business rules, we still have a mandated one-to-one and only one-to-one relationship because everyone must have a primary address.
Great, thank you.
Does that make sense?
I think so.
I think so too. I kind of made it up on the spot, but I think it works.
So in that case, what's the difference between the 0, 1, and the 1 symbol?
Yeah, so for that case, the address case, the rule is I must have an address.
Right.
If that rule didn't exist, then we could do a 0 or 1, because then I could be my person with no address.
But, well, then I was just wondering about the 1 at the top. So there's the...
Oh.
So wouldn't that be... Is that almost understood that that's a 0 or 1 also?
That's a great question. I don't know. I'll look it up. 1 versus 1 and only 1. I didn't even notice that.
I thought the one at the top is a mandatory one, no matter what.
Yeah, I'm trying to figure out how that's different than 1 and only 1, though. Maybe it is going to a forcing a one-to-one relationship across tables and not allowing many to one. Maybe. I'll look it up. I'll find the right answer. I could speculate probably all day. And I think that is it for today. This whole 2 classes a week is hard, but we'll make it work. Next week we will start doing, I will start a quiz next week. Everybody always says, are we going to have a quiz next week? Just assume you will. Because I like to do regular quizzes, just not to make them hard, not to make them tricky or anything like that, but just to make sure you're paying attention somewhat.
Professor, just a quick question for next week. It
Yep.
says to me normalization. Is there anything you could read just to kind of get ahead of that before we get a lecture? Any recommendation?
So I am trying to be more organized this time teaching the class than I was last time, which means I'm following the book. So next, let's see, where is normalization? Oh, I thought I was following the book. Where the heck's the normal? I saw it earlier. Hold on. Most people don't ask about getting ahead, so thank you. There we go. So it's on page 34, 35, 38. So it is early. Okay, good. I was right. Yes. So it is in chapter chapter 2 still in the book. Page 34 through Okay, the book material's not good on this, so I'm going to make it better. But that's where it is. It's about page 34.
Okay, thank you.
Yeah, we're going to talk about the 6 normal forms, as they're called. But again, I'm not an academic, so I'll quiz you on the first 2 or 3. Beyond that, unless you're building databases like the actual database engine, the first 3 are the important ones.
For the quizzes, is it recommended to go over the slides again? Just to refresh?
I would think so, yep.
Okay. Who's making?
Yeah.
So, we're going to be making the ER diagram.
You will be, yep.
Is there a specific software that we'll use to make them?
No,
Okay.
no, I don't care. Because in the end, basically, you'll be delivering me a Google Doc.
Okay.
So if you want to do it...
We had to use VCU when I took one of the 300 level classes.
Yep.
We weren't allowed to use anything else.
Oh, really?
Stupid.
That's that's silly. If you want to use Visio, great. If you want to use Draw.io, great. If you want to use, gosh, what's the other one? I just was looking at it today. Yeah, Lucidchart. That was the one I was looking at today. Yeah, there's plenty of option. And honestly, if you want to do it on paper and take a picture of it, I don't care. Well, no, you need to do it digitally, because I do care somewhat. Because I was reading our goals of the class or the program or something, and the number one goal is I need to measure your professionalism. And if I gave my boss a penciled piece of paper with an ER diagram on it, he'd probably fire me. I probably deserve it too. So yeah, we'll need to make it digital, and in the end, you'll just be embedding it into a Google Doc.
I have an answer for the one and only one versus one.
Oh, bring it.
So one and only one would, this is on Stack Exchange. Like a student has one and only one login ID, and then a one-to-one relationship would be like student and dorm room, because I guess the dorm room could change later.
Interesting.
That was the example.
Yeah, so what they're saying there is kind of the permanence of something, something that doesn't change. Yeah, student ID is a good one that never changes, even if you leave the school.
Number.
What's that?
Yes, it's a number.
Social security
Yep.
number, I think.
Oh yeah, no, I got it. I was thinking through it. But as a software engineer, I always do boundary testing on things, right? Even if it's just in my head. So my boundaries for social security number. Well, if you're a victim of identity fraud, you would end up getting another social security number, I think. But yes, you're right. That is a good example. The things that never change. Yeah, my employee ID at Capital One. I was there for a while. I left, came back a couple years later. Same employee ID. So that's the permanence of it. That makes a lot of sense. I like that.
Like a primary key.
Yeah, or immutable. It's really immutable. Right? Cool. All right. Well, I am going to stop my recording